Hi everyone. In this work, we explore a fascinating phenomena from high energy physics and cosmology. The paper is titled as Thin Wall Monopoles in a False Vacuum. Here, we numerically investigate the existence of thin wall magnetic monopoles in a false vacuum, which are characterized by a spherical region with a thin wall. Let's say that the radius of the wall is r and the thickness is delta, wherein the delta is much smaller than r and the entire thing is surrounded by pure abelian magnetic region. Before moving ahead, we need to define what are magnetic monopoles, which are essentially soliton solutions in non-abelian gauge theories with scalar matter fields, arising when a simply connected gauge group symmetry is spontaneously broken to include a UN factor. Their existence is linked to the non-trivial homotopy group, which is pi 2 of G mod H. In a false vacuum setting, such solitons could trigger decay, potentially converting the false vacuum into a true one through quantum tunneling. There have been previous works which have indicated that the thin wall behavior arises from gauge or the Higgs field dynamics, wherein the analysis relied on the proposition that the gauge field dynamics would essentially follow the Higgs dynamics. But this was never rigorously established. We numerically analyzed that these monopole solutions with the core in the true vacuum create sort of an outward pressure, resulting in the required thin wall behavior. Outside this wall, we see features of a pure abelian magnetic monopole. Now, our work focuses on the numerical treatment of such monopoles. We use the Georgi-Glashow model with 't Hooft-Polyakov monopoles. We employ a spherically symmetric ansatz to derive the equations of motion for the monopoles, which are essentially second-order coupled nonlinear ordinary differential equations. Now we are supposed to solve these equations to get the required monopole solutions. These equations describe how the scalar field and the gauge fields interact to form stable configurations. By carefully choosing the scalar field potential, we demonstrate that the existence of such monopoles under the thin wall approximation is very much possible. The choice of potential is critical to this work. The potential can be modified in an infinite number of ways. As we are not really concerned with renormalizability, we have chosen a potential for which the false monopoles exhibit themselves as thin walls, and this choice would create a classically stable false vacuum with a wide flat region, which has been previously explored in a variety of cosmological and supersymmetric models. The numerical analysis has been done in MATLAB, which confers the existence of such thin wall monopoles with a distinct core, a wall, and an exterior region. Further, using the energy density plots, we observe that the behavior is thin wall because it separates internal negative energy, which is proportional to volume, the positive wall energy, which is proportional to the area, the exterior large Coulomb energy, which is proportional to the inverse of the radius, of course. In a cosmological context, such decay could have profound implications for the evolution of the universe. These monopoles may offer quite some insights into the interplay between topological solitons and vacuum stability. Thank you.